Hello everyone, my name is Arslan Siddiq and I am going to present my work on trajectory estimation of vehicles. Here are some outlines of this presentation. We will start with the introduction, we will introduce the literature review, then I will explain the methodology, the results that I have got, then I will explain the conclusions, the future recommendations, and finally I will tell you the source code of this project. Let's start with the introduction. So the problem that we are facing is that in cities the population is increasing very rapidly and there is an urgent need for traffic surveillance systems and also for self-driving cars. Trajectory estimation is a very important part of these traffic surveillance systems and self-driving cars. But we have seen that in crowded scenarios, crowded and complex crossroad scenarios, like for example shown in this image and in this image, often the tracking algorithms fail. So that is the main target of our algorithm. These are some examples from UAD track dataset on which we will work in this project. The proposed hypothesis is basically based on a tracking by detection pipeline. It consists of three main stages. The first stage is the pre-processing of vehicles. The second stage is applying a vehicle detector. We are using mask RCNN benchmark and YOLO v3 for detection of vehicles, which will give us the bounding box locations of vehicles. These bounding box locations are passed to a sort tracker which will track the bounding boxes. These are the two main research contributions of this project. The first contribution is a detailed comparison of YOLO v3 and mask RCNN benchmark on UAD track dataset. The second is to test tracking by detection pipeline on crowded and crossroad scenarios. So in the literature review, we can see some data sets for vehicle detection and tracking, KTVN dataset, UAD track dataset. But in our case, we find UAD track dataset very good because it represents a crowded and crossroad scenarios. In the field of detection, we have several available options like RCNN family, SSD, YOLO, mask RCNN and Detectron, but most of these algorithms are slow. But YOLO v3 and mask RCNN benchmark have been found to be very good in terms of accuracy as well as speed. In case of tracking, we have several options like Kalman filter, particle filter, and sort tracker, etc. But most commonly sort tracker is used nowadays because it is fast and it's very accurate as well. There is some recent work done on the tracking of vehicles at crossroad scenarios in Chelyabinsk city of Russia. They also used a tracking by detection pipeline. They used faster RCNN together with sort tracker. So our work is very close to their work and we are trying to continue their work in the same direction. So the first stage in the proposed methodology is the pre-processing of vehicles. We can see in this image that there are some vehicles that are quite far away and quite occluded. There is absolutely no need to detect these vehicles. We just need to detect the nearby vehicles. So this is the reason that officially the authors of this dataset have suggested to ignore these image locations. So we get these ignored image locations from the annotation data file and we paint these rectangular boundary regions with white color and finally we get a pre-processed image. For the case of detection, I am using YOLO v3. YOLO v3 consists of three main stages. The first stage is a feature extractor which consists of 53 convolutional neural networks written in the darknet framework. Then the second stage is a feature pyramid network which basically does the main prediction at three different scales. And in the third stage we have prediction for large object, medium size and small size, and we combine all these to get a final output. For the implementation, I am passing the YOLO v3 pre-trained files, pre-trained weights and configuration file into the deep neural network module of OpenCV. Mask RCNN. Mask RCNN is basically an extension of faster RCNN, which consists of a two-stage processes. The first stage is to extract regions of interest using CNN networks and region proposal networks. And when we have these regions of interest, we apply fully convolutional layers to extract the bounding boxes and convolutional layers to extract the mask for every pixel. For the implementation purpose, I am using mask RCNN benchmark, which is basically a PyTorch implementation of mask RCNN algorithm. Since PyTorch is a low level library, so it is much faster as compared to the other frameworks like Keras and TensorFlow, etc. So mask RCNN benchmark is much faster technique. Detection. So we apply an object detector like YOLO v3 and mask RCNN benchmark, which gives us a prediction dictionary. It consists of bounding box locations, all the bounding box locations of every object in an image, and also we get bounding box locations from annotation data, which gives us a ground truth dictionary. We unpack these dictionaries and extract the bounding box locations. Then we have four main scenarios. One scenario is that we don't have a ground truth, we don't have a prediction, like the scenario of a road. So it is a true negative. We detect it true, but it is not our desired class. The second scenario is that there is no ground truth, but prediction is made. So this is a false prediction and this is false positive. If there is a ground truth but prediction is not made, then it is false negative. And the third scenario is that there is a ground truth and one prediction is also made. So this is the case that I am interested. But we need to do one more check, and that is we need to calculate intersection over union of prediction bounding box and ground truth bounding box. If this IOU value is greater than a particular threshold, which is 0.7 in our implementation, then it is considered a true positive, and if it is less than this threshold, then it will be considered a false positive. The tracker that I am using is sort tracker because it is real time and very accurate. It as an input, it takes detection of previous frame and the current detection values. Then it uses Hungarian algorithm to associate bounding boxes between current frame and the previous frame. When after the association is done, we use Kalman filter to track the associated bounding boxes. Our Kalman filter design is basically a constant velocity model. The state consists of 8 variables. The measurement consists of 4 variables. This is the state transition matrix, this is covariance matrix, and this is the state to measurement matrix. The dataset that I am using is UA-DTRAC dataset, which consists of 10 hours of videos captured on different locations in Tianjin and Beijing. This dataset was chosen because it represents a challenging and crowded scenario. Each image size is 960 by 540. If we look at the dataset, there are 4 main categories of vehicles: cars, buses, vans, and others. So since our object detector can only recognize car and buses, so we are only using these two types of vehicles, and we are ignoring the van and others. In order to measure the performance of detection, we use several detection evaluation metrics. The first one is intersection over union. The intersection over union, we have 2 main cases. We have a prediction dictionary, we have a predicted bounding box, and we have a ground truth bounding box. The intersection over union is basically a ratio of overlap region to the area of union. These 2 tables represent the average intersection over union values using YOLO v3 and mask RCNN benchmark for different weathers. And if we make a comparison, we see that the performance of mask RCNN benchmark is better than YOLO v3 for all weathers. Precision recall curve. This is another detection evaluation metric, for which in which basically we plot recall on x-axis and we plot precision on y-axis. In order to calculate precision and recall, we need true positive and false positive, which we calculated using the detection pipeline that we have seen in the previous slide. After we calculate precision and recall for every bounding box, we make the precision recall curve. The area under the precision recall curve represents the average precision value for a particular class, and the arithmetic mean of all these average precisions is mean average precision. So this mean average precision is the most important object detection metric, which is mainly used to compare the performance of object detectors. For our algorithms, we get some results like this, in which we see that the performance of mask RCNN is better than YOLO v3. As we can see that the value of MAP for the orange bars is always higher than the blue bars. In order to perform tracking, we perform experiments on first 120 frames of this particular sequence from cloudy portion of test data. The reason to choose this particular sequence is that it represents a crowded and crossroad scenario. And these are some of the results. So this video represents the tracking on these 120 frames, and this is basically a comparison of ground truth with the predicted trajectory. The black represents the ground truth trajectory and green represents the sort tracker based trajectory. So we see that we have done it pretty much accurate. I think it's very much overlapped, so this algorithm is pretty much accurate. And the white rectangles, these represent the region that should be ignored. Furthermore, in order to measure the performance of tracking evaluation, we use the evaluation protocol that has been suggested by these authors. What they do is that they measure the Euclidean distance loss. The Euclidean distance loss is basically the distance between the ground truth trajectory and the detected trajectory in units of pixels. So for the same 120 frames that in which we are performing the experiments, we get some results like this, which represents the RMS error per detection in units of pixels between the detected and ground truth trajectory. We have one tracker, SORT, and we have two main detectors, YOLO v3 and mask RCNN, and we see that the error for mask RCNN is less than that of YOLO v3, which means that if we use mask RCNN as a detector, then we get more accurate results. Finally, coming towards the conclusions, the one conclusion that we draw is that mask RCNN benchmark outperformed YOLO v3 in detection. In terms of future recommendations, the main thing that we have observed is that the detection of vehicles from side pose is much poor as compared to the front and back pose. So and also we performed experiments on our low-end machine. Basically it's my laptop on which I have performed experiment. So the speed is around 2 frames per second, mainly because of the slow detection stage. So basically we need more accurate and fast detectors, particularly trained for vehicle detection tasks, and we need accurate detector for side poses mainly. The front and back are considerably accurate and they are fine. Source code, the source code for this project is available on my GitHub repository, and the video demos are available on my YouTube channel. These are some of the references, and finally, thank you very much. If you have any questions, feel free to ask.